Hello everyone. Let's try to have the area under the curve in the polar coordinates. Here is the curve in the polar coordinates. Yes, in this case, the function of theta is the function of the curve. So r equal to the function of theta will be the curve equation. Fine. Now, before we start going through the polar coordinates system to find the area, let's have the link between the rectangular coordinate or the Cartesian coordinate and the polar coordinate. As you see here, the origin in the Cartesian coordinate, we call it the pole. The positive x-axis, we call it in the polar coordinates, we call it polar line. As you see, the r is a line or the segment between the origin into the point. Theta start from 0 in the polar line or the Cartesian x-axis to the line linking the pole to the point. So x will equal to r cosine theta and y equal to r sin theta. If you have x and y, you can find theta from this relation and you can find r from this relation. So theta will be tan inverse y over x and r square will be x square plus y square. So r will be the square root of x square plus y square. Let's go and see the formula of the area in the polar coordinate. Let's have a curve given in the polar coordinate. So we take a tiny piece of the area under the curve. So this tiny piece has an area equal to half r square d theta, where d theta is a small angle. Okay. Now, if we would like to have the total area under the curve, we are going to integrate, because the integration is the sum of the slices of the area under the curve. So the area under the curve in the polar coordinate is half r square d theta, where r is a function of theta describing the curve in the polar coordinate. Fine. What about if we have two curves and we would like to have the area between the two curves? As you remember, in the Cartesian coordinate, we have the area under the upper curve minus the area under the lower curve. Yes, exactly. Here we are going to do the same thing. So the area under the upper one, which is r2 as a function of theta, so you will have the area under this one is half r2 squared, and the area under the r1 will be half r1 squared. So subtracting the upper area minus the lower area, we will have the area between the two curves, exactly similar to the Cartesian coordinate, but in the polar form. Let's have this example. If you are going to have the area inside the or bounded by the curve r equal 2 times 1 plus cosine theta, and we call this one the cardoid. Because you are going through the whole curve, which covering the 4 quadrant of the Cartesian coordinates, and we start 0 as a theta from 0 from this positive x-axis, and we end up at the same point, which we go through the 2 pi angle. So the area will be half r squared d theta from 0 to 2 pi. Those are the main point. You are looking for the boundary of the integration, so you seek for finding the value of theta from the starting point to the end point of your area. Now you square the r square and multiply it by half. So when you square 2, you will have 4. When you square 1 plus cosine theta squared as a complete square, you have the square of the first part plus 2 times the first times the second plus the square of the second one. Yes, integrating from 0 to 2 pi, and we agree because we are covering the whole 4 quadrants, so we integrating from 0 to 2 pi. You can integrate each part except cosine square. So you have to substitute cosine square using the trigonometric identities. Cosine square theta equal to half times 1 plus cosine 2 theta. Now you cancel out this 2 by 2 and you multiply this 2 inside. So you end up with 3 plus 4 cosine theta plus cosine 2 theta d theta. This integration is easy because the integration of 3 is 3 theta. The integration of cosine theta is sine theta. The integration of cosine 2 theta is sine 2 theta over the derivative of the angle, which is 2. So plug in the upper value 2 pi minus the substitution of the lower bound, which is theta equal to 0. You end up with 6 pi unit square as your area inside this cardioid. Let's go for that second one, which is another type of curve given by r equal to 2 cosine theta plus 1. It looks like that. So how to find the area inside this small one here? So yes, you square your r and then you're looking for the boundary of your integration. Look at this one. The boundary of your integration from 4 pi over 3 into 2 pi over 3. But this required area, you can slice it into 2 pieces. From theta equal to 2 pi over 3 till theta equal to pi. So yes, you can have double of this one, give you the total area. This is why in your formula for A, the area, you don't have the half, because you get half of the boundary. This is why you have A equal to r squared d theta without the half. Yes, exactly. The area is double of the area bounded by theta equal to pi over 3 into pi. And we know the formula of the area is half r squared. So you double this one. So the half will be omitted. Now you, as we have done before, you change cosine square theta into half times 1 plus cosine 2 theta. This integration is very easy, and you end up with the area pi minus 3 root square 3 over 2 unit square. Let's go for the last one, but now we are not going to have the area bound under the curve, but we are going to have the area bounded by two curves, or the area between two curves. Yes, we have the circle and cardioid, and we are looking for the shaded area, the blue shaded area. Yes, we are thinking about the upper one is R2, which is equal to 1. So the area down this curve is half 1 squared d theta minus the area of the inside one, which is the cardioid, so half times 1 minus cosine theta square. Yes, I hear you. You are looking for the boundary of your integration for theta. So because we're covering the right half of the rectangular or the Cartesian coordinate, so we go from minus pi over 2 into pi over 2. Yes, the area is half r2 square minus r1 square. R2 is the outside one, which is the 1 square, minus the inside one, which is the cardioid 1 minus cosine theta squared, and we square it as a previous example, and we can integrate cosine theta as a sine theta, but we have to change cosine square theta using the trigonometric identity into half times 1 plus cosine 2 theta. Now, yes, you can integrate cosine theta into sine theta. The integration of minus half is minus half theta. The integration of cosine 2 theta is sine 2 theta over 2, and you already have 2 here, so it will be 4. Substitute by pi over 2 first, and we know sine pi over 2 is 1. But when you substitute by pi over 2 in sine 2 theta, we will have sine pi, which is 0. Okay, when you substitute by 0, sin 0 is 0 and sin 0 is 0. So you end up with 2 minus pi over 4 units square as your area. You have too many questions here. You can try it yourself, and you have to distinguish between the area under the curve and the area between two curves. Thank you.